In this last example, we're going to take a look at an application of utilizing the chain rule. And a lot of times we're able to use the chain rule in partial differentials. And we just want to verify that given any function z equals fxy, where x is the parameterized r cos theta and y is the parameterized r sine theta, we want to show that this identity is valid. So this could be a really tricky problem if you don't even know where to start with it. And unfortunately, there's not much to really do on the left-hand side, all right? Because what we're trying to do in this case is maybe try to make the right-hand side look like the left-hand side. So let's start with that. And let's find a couple of the partials immediately. So we know that the partial of x with respect to r is going to be cos theta. We know that the partial of y with respect to r is going to be sine theta. We know that the partial of x with respect to theta is going to be negative r sine theta. And we know that the partial of y with respect to theta is going to be r cos theta. All right? And that's just using these as our derivatives. Now what we can do is we can use the chain rule on both of these. And I'm going to start with this one. All right, so I'm just going to do these in pieces. All right, so everything I do in red is going to be partial of z with respect to r. So partial of z with respect to r can be written by the chain rule using a total differential as the partial of z with respect to x times the partial of x with respect to r plus, because that's our function of x, now we need our function of y, partial of z with respect to y times the partial of y with respect to r. And the good news is we already have these two. If you look right above, we have both of those as cos and sine theta immediately. All right, so this is the same thing as partial of z with respect to x times cos theta, and then plus the partial of z with respect to y of sine theta. And what we're looking for is we're looking to square this. All right, so if you look at our identity, it says partial of z with respect to r squared. So we're going to square everything, which means we have to square this. And unfortunately, what we're going to end up with is we're going to end up with a pretty nasty FOIL here. All right, but we're going to hold on to it. So by FOILing this out, we're going to get partial of z with respect to x squared times cos square theta plus, so remember we just double the product, so that's going to be 2 partial z partial x partial z partial y cos theta sine theta and then finally plus partial z partial y square, and then we're going to multiply that by sine square theta. All right, so let's hold on to this. All right, and again, that's all equal to this animal right here. All right, unfortunately, we still now have to worry about this. So let's just start by finding partial z partial theta. Then we can worry about the 1 over r squared and then the square. Okay, so partial z partial theta by chain rule is partial z partial x partial theta. And since it's a total derivative, partial z partial y times partial y partial theta. But we already know partial x partial theta, partial y partial theta. Right? So partial x partial theta is negative r sine theta, and then we have r cos theta. All right? So we're just going to substitute those. So this is going to be equal to the opposite of partial z partial x times cosine theta. Let me just make sure that's true. Yep, r sine theta. Plus partial z partial y of r cos theta. All right, but similar to the last example, we just don't want that. Not only do we want that squared, but we also want to multiply that by 1 over r squared. All right, so we're going to have to do some more algebra. All right, so let's just square this out because we want this squared. And we still need the 1 over r squared, so we're going to worry about that at the end. So let's just do this. So we're going to square the first and the last terms. So that's going to be partial z partial x squared r squared sine square theta. We're going to double the product. All right, so that's going to be minus 2 partial z partial x partial y, partial z, partial y. We have r times r, which is r squared, and then we have sine theta cos theta. Right? And then we're just going to square the last term. So we're going to say plus partial z partial y square r square cos square theta. All right, so that's the square of everything. But remember, we have to multiply this by 1 over r squared. All right? And that's good because if we do that, that just means all the r squareds are going to go away. All right, so if we do that, this implies that 1 over r squared times partial z partial theta square is going to be equal to everything above except for the r squared. So that's going to be partial z partial x square and then sine square theta minus 2 of partial z partial x partial z partial y sine theta cos theta. And then finally we have our partial z partial y square, and we have our cos square theta. Alright, so now if that's not enough, we have to take what we just found in green and we have to add that to what we have all the way up here in red. And then hopefully it equals that identity that we had in the beginning. Alright, so I'm just going to add these together, and I'm going to see if I can just kind of move this down. Maybe it'll work, maybe not. So let's see. Let me see if I can cut and paste this. That way we don't have to redo this. Alright, so copy it down here. Ah, success. Alright, so let's see if we can start adding some like terms together. Alright, and it might be a little bit more difficult than anticipated. So, alright, so use one more color here so we can kind of identify these like terms. Now we have a partial z x squared sine square theta and a partial z x or partial z partial x squared cos theta. All right, so let's just add those below. So we're going to have partial z partial x square sine square theta plus partial z partial x square cos square theta. And clearly we can see what's going to happen here. If we factor out this squared derivative, we would get partial z partial x squared times sine square theta plus cos square theta, which is just going to be equal to this partial z partial x square. All right, so let's hold on to that. And by the way, remember, we have to add these together. All right, so I probably should have said that we're adding these. And the reason we have to add them is because we go all the way back to the beginning. And remember, we're adding them due to this PDE. That's what we're doing. So we're just adding this side and this side together. All right, so far so good. Let's take a look at the two terms again. And I want you to notice that we have a negative 2 partial z partial x partial z partial y sine theta cos theta, and then we have a part of positive 2 positive or partial z partial x partial z partial y sine theta cos theta. Mercifully, those cancel out. All right, so notice we have a negative, and that goes away. And then the last thing that we notice is that we have a partial z partial y square cos, partial z partial y square sine, and we can just add those below. Okay. So we're going to say, let's just use one less color. So now we're going to say partial z partial y. And I can't remember which one went first. So we have this cos square theta, or sorry, we have the x first. So, oh, I'm sorry, partial z partial y square cos theta. All right. Cos square theta plus partial z partial y square sine square theta. And we can clearly see, just like what happened before, if we factor out the partial z partial y square, we're left with the trigonometric identity, actually Pythagorean to be specific, cos square sine square theta, and that just equals 1. So now we're left with just the partial z partial y square. All right, so the sum of everything, we're going to say, if we just go back, so we have this left over, and we have this left over, all that's left is that the sum of, now remember at the very, very beginning, we had partial z partial r square plus 1 over r square partial z partial theta square. All right, so that's all the way at the beginning, right here. And after all of that work, where we found all those partials, the only two things that are left are partial z partial x quantity square, partial z partial y quantity square. So that's going to be equal to partial z partial x quantity square plus partial z partial y quantity square. All right, and let's hope that that's the identity that we wanted. All right, so we're going to go again all the way back to the beginning. And if we go all the way back to the beginning, we wanted to show that it equals partial z partial x, partial z partial y, both squared, and the sum of those. And so it looks like that's exactly what we wanted. All right, so again, this is an application that we can utilize of our chain rule to be able to verify partial differentials. And remember, this is true, go back, for any function z of fxy, as long as x is parameterized as r cos theta and y is parameterized as r sine theta. And that's one of the things that you all are going to see when you take partial differentials, is that a lot of times there's these unknown families of functions, all right, that are going to constitute part of your solutions. And this just helps you to verify that it is indeed part of the solution set.